We're going to be reading the paper, Can Baby Universe Absorption Explain Dark Energy? Now, this article, caught my eye because in their abstract, they talk about the DESI 2024 data, which has been on my mind quite a lot for the last 5 months or so. So, we're going to be talking about this, so let's jump right in and read the abstract. Hopefully this is visible for everybody. Yeah, DESI. DESI is it's the source of my interest. It has been proposed. Oh, by the way, this is by Varun. Oh, that was a mistake. Muralidharan and James M. Cline. These both of these people, or I guess, oh, I guess they're both in Montreal. Okay. Right. So it has been proposed that the accelerated expansion of the universe can be explained by the merging of our universe with baby universes, resulting in dark energy with a phantom-like equation of state. I'll explain what equation of state is later if they don't. However, the evidence in favor of it did not include the full set of cosmological observables. This is like data. I'll zoom in a bit. We'll be zooming in more in a minute, once we get through the abstract. Here we examine the implications of this model for both early and late universe cosmology using data from Planck collaboration, DESI 2024, and other experiments. We find that the pure baby universe model gives a poor fit to current data. Extending it to include a contribution from the cosmological constant, we find two allowed regions of parameter space, one close to lambda CDM and another with lambda negative plus the exotic dark energy component. The two regions can be significantly favored over lambda CDM depending on the choice of supernova datasets, and they can ameliorate the Hubble tension to the level of 2 sigma, depending on the supernova dataset. The model with lambda less than 0 features an equation of state W of A with a pole singularity at early times. Okay. So basically, they have this model where our universe merges with baby universes, and I guess that causes dark energy somehow. I don't understand that, but hopefully they'll explain. And they find that if you try to use new data, you're not actually going to get good agreement if you just use that model without any cosmological constant. But if you invoke a cosmological constant, either positive or negative, you end up with two things that do fit the data. So hopefully they're going to explain what we're doing, and let's jump right in. So I'm going to zoom into each column. Again, this is a short paper, so it is column by column. Hopefully this will be good enough. I'm also going to take my light and move it so it's not in the way so that I can read properly. Hopefully my lighting is sufficiently good. Yeah, that's fine. Right. Hopefully, can everybody see this all right? It should be big enough, I hope. Right, okay, it looks like we're okay. This is a preprint. This has not been, well, I don't actually know. This may have already been accepted at a journal, but as far as I know, this is a preprint, which is quite new. Right, so although the cosmological constant is the simplest description of dark energy and still gives a good fit to cosmological data, there remains steady interest in possible deviations from the time-independent dark energy. And many theories of modified gravity have been studied with respect to their ability to better describe the observations. In particular, the Hubble tension problem has given an impetus to certain classes of early dark energy, as have been reviewed in reference 1. Let's go take a look at what reference 1 is. Reference 1 is, I guess it's just a reference about in the realm of the Hubble tension review of solutions. Okay, they're just talking about various solutions for the Hubble tension, fine. These have the features that the main modifications to the expansion history occur at high redshifts and have been shown to be the most promising class of models for ameliorating the Hubble tension. So the idea is that we're thinking that maybe if you change the rate of expansion in the early universe, but kind of leave today alone, then we can resolve the Hubble tension. At least that's what they're saying. Many of the proposed modifications of gravity involve ad hoc functions of the Ricci scalar replacing the simple Einstein-Hilbert action for gravity, and are lacking any plausible ultraviolet completion. So to be clear, what they're doing is they're taking the, if you take the normal Einstein field equations, normal general relativity, the action principle is just related to the Ricci scalar, which is a measure of how curved spacetime is. However, if you instead just take a function, like the Ricci scalar squared, or the cosine of the Ricci scalar, or whatever it might be, you can get things that seem to resolve the Hubble tension, but they're ad hoc, and there's not really a good justification for why they take that form. So the point is that that's really what they're saying in this first sentence. In contrast, references 2 and 3, also see also 4 and 5, put forward a model of quantum gravity that has a quite concrete and physical basis, namely the absorption and emission of baby universes by the observed universe. So I don't know what a baby universe is. Let's go take a look. Is the present acceleration of the universe caused by merging with other universes? This is fairly recent, actually. 2, 3. Yeah, this is recent. So I'm actually not familiar with that. Maybe we can read about that next time. Hopefully they'll explain it here, though. It leads to a modified Friedman, right, so emission of baby universes by the observed universe. It leads to a modified Friedman equation for the expansion of the universe, which depends only on the coupling constant g, whose sole energy contributions at late time is from the non-relativistic matter, baryons plus dark matter. The accelerated expansion arises through a modification of the Friedman equation rather than through an explicit dark energy contribution. So I guess what they're saying is that the modification that they're going to be working with, which is a modification of general relativity, affects not the amount of dark energy that there is, but rather the what am I trying to say? Rather the way that dark energy affects expansion. At least that's the idea. Reference 2 found evidence in favor of this model using a limited subset of available cosmological data and concluded that it gives a good fit if the Hubble parameter agrees with late time determinations. H0 is 73 kilometers per second per megaparsec. Just so everybody knows, the Hubble parameter is something like, it tells you something about how fast the universe is expanding. Roughly, it tells you that if something is 1 megaparsec away, it tells you how fast the distance between you and it is expanding. So if it's 1 megaparsec away, then the observed redshift of the thing that is that far away would correspond to a recession velocity of 73 kilometers per second. So at 1,000 megaparsecs away, or a gigaparsec away, you would get 73,000 kilometers per second, which is like a third the speed of light. Or a fourth the speed of light or so. And to be clear, a gigaparsec is like 3.2 billion light years or something, 3.3. So this gives you a reference for how fast the universe is expanding. Now, their analysis was done without using without using CMB data, hence it is of interest to know how it fares against all available data. We modified the Cobaya code in order to test the model's predictions with respect to the standard set of observables, described in section 3a. Okay, hopefully they'll explain what that is. In order to compare it to the standard lambda CDM, which is the standard model that we have of cosmological evolution, it's also called like the standard model of the Big Bang. In order to compare it to a standard lambda CDM, we extend the model with a parameter f sub lambda that represents the fraction of the dark energy that comes from cosmological constant rather than from baby universe absorption. So what they're going to do is they're going to add an extra layer. They're going to say that there's baby universe absorption, and then there's also some amount that comes from just regular dark energy, like regular cosmological constant dark energy. We will show that f lambda must be greater than 0.64, meaning that the expansion has to be at least 64% from dark energy, or less than 0.16, negative 0.16, meaning that you actually have to have like a negative cosmological constant, which is kind of not quite a contraction, but it's, yeah, but it's kind of like a traction in some sense. Hence, the pure baby universe scenario with f lambda equals 0 is ruled out. However, we find some admixtures of cosmological constant and baby universe dark energy that can give significantly better fits than lambda CDM, depending on which supernova data are included. So, what they're going to show is that there's like some mix of dark energy plus baby universes that better fits the data than just dark energy in the standard cosmological constant sense. So that's interesting. Let's see what they have to say. So, they're going to explain it to us. Great. We start with a recapitulation of the baby universe dark energy framework. It is a mini superspace model. I should explain what that is. It is a mini superspace model where the volume V, which is A of t cubed over kappa, of a given topologically distinct universe, kappa here is just a constant, is the dynamical degree, where the volume is the dynamical degree of freedom. So, okay, I need to explain what a mini superspace model is. So, A mini superspace model is just a model where really the only kind of like dynamics of the universe involves the size of the universe. So it's just expanding, contracting, maybe it's oscillating, whatever it's doing. That's what makes it a mini superspace model. It doesn't have anything to do with supersymmetry. It's just called a mini superspace model because you're only worried about how the universe is expanding and contracting. You're not worried about like one part is growing faster than another, or maybe there's like galaxies doing orbits. We're kind of like washing all of that away. So we have a volume that tells us about the mini superspace universe, the volume of the mini superspace universe rather. And that volume then changes. It has a rate of change. And in some sense, we call that rate of change the conjugate momentum. That's the way of thinking about it. So we say its conjugate momentum is related to A dot. A dot here, this is the, so we have A here. This is the expansion rate. No Grassmann numbers, no. So A here is roughly the size of the universe, or rather it's kind of like the diameter of the universe. And so its volume would be the diameter cubed in some sense. It's like a rough estimate of it. It's not a rough estimate, but like it's a measure of the diameter of the universe. And so the idea is that the rate of expansion should be related to the rate at which the diameter is growing. And that's what A dot is here. A dot is just the rate at which the diameter is growing. And so the conjugate momentum is related to the rate of change divided by the rate of change of the diameter divided by the diameter. So it's roughly the fractional rate of change. How fast is it doubling, roughly? Which is the Hubble constant. And they say that it's related to the conjugate momentum by some function, or rather the derivative of some function. I don't know where this is coming from, but roughly this is just what their model says. So I don't know, I guess we just believe them, or we could go look at the references, but we're just going to believe them. And this is just some function f. Okay, they're actually going to define what it is. So for a given function f, equation 1 can be solved to find p as a function of a dot over a. So this is just saying there's going to be a relationship between the sort of the rate at which the universe is like this kind of conjugate momentum, which it's more than just the rate of change of the scale factor, but it's related to the rate of change of the scale factor. But it's going to be related to it by this equation, in fact, as long as you know what f is. So then we have that the modified Friedmann equation is then given in terms of the energy density of matter and radiation emitting any vacuum energy by... Oh, okay. Wait a minute, now I'm confused. So what's confusing me here is that the modified Friedmann equation should depend on, I mean, we can go look at what the modified Friedmann equation is, but the modified Friedmann equation should either have a dot or a double dot, depending on which Friedmann equation they're using. But for some reason, they have no derivatives of a, which is a little bit confusing. So they just say the modified Friedmann equation is then given in terms of the energy density of matter and radiation emitting any vacuum energy by f of p. So this I don't follow. Maybe they'll explain it better. If they don't explain it better, then we will we'll go and probably look at the reference. I'll be right back. I have to go turn on the AC. Okay. So, p is not a function, it's a variable. It's treated as like a dynamical so it's f prime of p. That's the thing that's confusing. If it wasn't f prime of p, then it'd be fine. But they're saying that f of p gives the modified Friedmann equation, not f prime of p. I don't know if that's a typo. I suspect it's not. I suspect I'm just missing something. But we can keep reading and we'll see if we can make any sense of it. Right, so we have that the modified Friedmann equation is then given in terms of the energy density of matter and radiation emitting any vacuum energy by this equation. And so they say, look, the conjugate momentum is in some sense related to the rate of expansion because it's the conjugate momentum of the volume. So if you think of position, if you think of the variable position for like some object, its conjugate momentum will be its regular momentum, which is related to its speed. So if the volume is like the position, then the rate of expansion should be like the conjugate momentum. And then they're just saying that in some sense, some function of the rate of expansion is related to the energy density of the matter here and the energy density of the radiation. That's what these two symbols mean. This is rho sub m, energy density of matter, and rho sub r, energy density of radiation. And they say that the function f of p encodes an extra nonlinear term in the Hamiltonian of the quantized mini superspace model. That represents the effect of an initially disconnected region of space, a baby universe, merging with or being emitted by the observable universe at some time in the past, parameterized by the volume v of the observed universe. P and rho look too similar. That's true. So, and they're going. How does quantized mini superspace work? I have no idea. Actually, I have absolutely no idea, and I actually might want to go read that article because it might be relevant for the work I'm doing. But anyway. One can picture it as a local interaction in which two universes merge into one, or one splits into two with some interaction strength g, that is dimensions of mass cubed. This is so funny because they're treating it like scattering. They're treating universes as if they're scattering. I mean, it's beautiful. I'm gonna have to go read the articles. Right. It's very, very bizarre. But let's go with it. Let's see where it goes, okay? The sign of the coupling determines whether the interaction represents merging, g is greater than 0, or splitting, g is less than 0. I'm going to go look at this reference. This footnote is useless. Footnote 1, see footnote 5. Nah. That's so not helpful. Right. So, its magnitude could naturally be exponentially suppressed by the action of the gravitational instanton that describes a baby universe coupling. That's a hell of a sentence. What does that mean? So, yes, we have this local interaction. And they're saying it could be exponentially suppressed by the action of a gravitational instanton. Why would that happen? I guess, are instantons exponentially suppressed? I guess they are. I guess that's why they're rare, right? Okay, I'm just gonna believe them. I don't think that that's actually relevant for the rest of the paper. If it becomes relevant, we'll go look. An instanton is like a... It's very hard to explain. It's related to a soliton, but in time. Maybe there's a good diagram. Let's pull up Wikipedia and we can... Actually, I'm not going to get distracted. Anyway, this could in turn explain the small magnitude of the dark energy, assuming that the cosmological constant vanishes. Okay. We recall that Coleman suggested a mechanism by which baby universe interactions could select vanishing cosmological constant as the preferred state of the universe. Okay, I think that that's just kind of a side thing. This framework can reproduce the standard lambda CDM model if one turns off the coupling G associated with the interaction of baby universes and makes an appropriate choice of the function f of p. So we're going to say that there is no coupling with baby universes, so you turn off the coupling G, and then you just choose f of p to be this. This is what you get. Okay, I mean, I guess you can do that, and then it implies that p is minus 2h, which I think is fine. The Friedman equation 2 is then h squared is this guy, which is the expected result for vacuum energy. Okay, yeah. For vacuum energy, rho of lambda is lambda over kappa coming from a cosmological constant lambda. So yeah, so if you turn off the coupling constant G, and then you choose f, you can actually make it so that you reproduce the normal model. So this is saying that with the right choice of f, you can kind of adjust your model to do a whole lot of things, right? So now they're going to consider not doing that. Let us now consider a universe with vanishing cosmological constant lambda equals 0, so they're not going to do the normal thing. And they are going to have the merging of baby universes with a coupling constant g greater than 0 as the sole source of dark energy. In this case, f of p is given by this function, which seems wildly ad hoc. But they just say, look, apparently it's derived here. You know what? I'm actually going to pull up this article because it seems really cool, and I want to read it. I'm going to pull up this one too. Why did they spell the name differently here and here? Oh, they've published a lot on this. Anyway. Yeah, okay, so I'll read those later. Right, so you get this formula for F1 of P. If you have, and I don't know where this comes from, but apparently it comes from their model. Actually, let's just go look at the reference just to see if that equation actually shows up. So they are doing like a mini superspace quantization, which is cool. That's a fun picture. I love pictures. And then so then they have that's just a solving for an identity. Where does this formula come from? Here, it's this one. So yeah, it's that one. But they have a minus sign. P plus alpha. Yeah, why do they have a minus sign? Okay, well, they differ by a minus sign. Do they actually talk about it anywhere else? They have a minus sign there. Maybe okay. It's just because they have a relative minus sign difference. So the only difference between that paper and this paper is that there's a relative... Nope, never mind. They have the same minus sign. All right, let's keep digging, see if we can find where that formula comes from. I mean, it could just be a minus sign difference. Wow, this is messy. Okay, so it's close enough that I'm willing to let it go. We'll just grant it, suppose it's right, and see what we can do. So this is the F of P that they're going to use for the merging baby universe model. So basically, there's a whole bunch of baby universes that are merging with our universe all over the place, and that's causing the expansion somehow. Which, okay, I guess. Sure, let's just suppose that that's true. What does that say? Then, by plugging that into this equation, and into this equation, then you get at early times P is large, so this is the conjugate momentum of the volume of the mini superspace baby universes, and one can expand equation 5, which is... Where's equation 5? So this is at early times, so this is when the universe is growing quickly, hence P is large. One can expand equation 5. I guess you're expanding in large P. So you expand, you expand in powers of alpha over P. Okay, that's fine. Yeah, so expand in large P. And you get this, which is much simpler. That's acceptable, I guess. So all they're doing is they're saying that this is a good approximation of F1 when P is large. So that's the F2 that they're going to use. Yeah, we're talking about a large P here, obviously. Obviously, we're talking about a large P. They also considered this in references 2 and 3, so that's good. By comparing to equation 3, which is somewhere, let's go look at what equation 3 is. Equation 3 is this one. Okay, so let's compare those two. I don't know if you guys can see this, but they're actually fairly similar. Namely, that you get 3/4 P squared in both cases, and then you get 2 over G, and you get minus lambda. So what they find is that one sees that the baby universe model resembles lambda CDM, but with dark energy that is growing with time, since P is proportional to minus H, is decreasing. So the lambda is getting stronger with time, which isn't what the DESI result says. Anyway, for convenience, we will refer to the two alternatives 5 and 6 as Model 1 and Model 2 respectively. Fine. Although Model 2 will turn out to give a worse fit for the data, it provides a simple qualitative understanding of the effects of the exotic dark energy source. So that's neat. So roughly they're saying that, at least at early times, the model that they just provided can be seen as an increasing dark energy model, which is cool. They also say that the above formalism can alternatively be understood in terms of the ordinary Friedmann equation, h² equals kappa rho crit over 3. This is just relating the expansion rate to the critical density by defining an equivalent formal dark energy density as this. So you just take the critical energy density, subtract off the matter and the radiation, and you get a formal dark energy density. And then you write what h is in terms of f, and you get the f prime of p squared over 3 kappa from equation 1. That's here. You're just plugging in h here into this equation, and you get this equation. And then rho m plus rho r is f of p over kappa from equation 2. And so you end up with, so you plug that in here, and then you end up with this equation. You get a dark energy density in terms of p, f prime of p, and f of p. Okay. Let's try to make sense of this, where rho sub f is the dark energy density coming from baby universe absorption. So basically this is saying that there's an equivalent dark energy for baby universe being absorbed. So each baby universe that's absorbed, it gives like a certain amount of dark energy, essentially. This form is useful for comparing the baby universe model to other dark energy models, including the cosmological constant. So essentially what you would do is you would look at this quantity, and this would tell you how much dark energy there is, and you can compare that with other models of dark energy. That's the idea. Rather than just kind of trying to like match. So this would tell you about dark energy. The density of dark energy. The value of the coupling constant G, alternatively alpha, because remember, G and alpha are related. And the present value P naught of P are related to the observables rho m naught and H naught, the current matter density and the Hubble parameter through these. So I guess that this is probably fairly straightforward. How do we get this? So f of P naught is... So I'm just trying to look at how we get this. So what do we know? We know that f of P naught is going to be... So f prime of P squared over 3 kappa, that should be related to the critical energy density, or to h squared. So if you plug in P naught, then you'll get H naught. So that's where this equation comes from. And then this equation comes from substituting in f prime of P naught squared into this equation, substituting in what we know rho sub f to be from this equation, and then solving for f of P naught. That's what they're doing here. That's how they get these two equations. So this tells us what f of P naught is and what f prime of P naught is, which is useful. In particular, f prime of P naught is basically the negative of the Hubble constant, and f of P naught is related to the matter content, which is interesting. Why all these substitutions? Just as a way of kind of understanding what's going on now. That's the idea. They also say, although it has a negligible effect, we also include the contribution from the radiation energy density in a rho sub m naught. Okay, so it's not just the matter, it's just the radiation. It's the radiation plus the matter. But there's like no radiation right now, so it's fine. Right, equations 8 can be numerically solved to determine G and P naught. So what do we have? We have equation... What does it mean to solve... You can't numerically solve this. What? What does that mean, numerically solved? I mean, like these are just initial data, but what's the differential equation? Is it this? Is this the differential equation? So they're saying equation 8 can be numerically solved to determine G and P naught. Therefore, models 1 and 2 do not have any additional physics parameters beyond those already present. Maybe they'll make sense of it. Beyond those already present in lambda CDM. Lambda is replaced by G. So how do they... What are they solving for? Because F1 and F2 are already given. Yeah, what's the... What is... I mean, they're solving for f of p. But where's the differential equation that defines f of p? Is it... Is it this equation? Because this is a differential equation in F, but rho sub F is not fixed. I don't know what else they would be solving for, though, which makes this kind of puzzling. Well, if the readers are watching this at some point, specify, what are you solving for? Well, look, because these are like, oh, I'm so stupid. I'm so dumb. Look, we know what F1 and F2 are. These are just messy equations. So you can just solve for P naught and G in these equations, right? This is just this is an algebraic equation here. This isn't a differential equation, but they're messy, and so you solve them you solve them numerically instead of solving them like by hand algebraically. That's all they're doing. That's all they're doing. Okay, so if you're watching, authors, I retract that statement. I retract the statement that you need to be more specific. They're just solving. Look, they just take F1, and they just take the derivative, and then they just plug it into here, and then you can solve for P naught and alpha. Anyway, right. So then they say, therefore, models 1 and 2 do not have any additional physics parameters beyond those already present in lambda CDM. Lambda is just replaced by G. Okay. For greater generality, we define model 3, so they're adding one more model, by introducing a parameter f sub lambda that interpolates between model 1, which is supposed to be the more accurate representation of baby universe absorption, and lambda CDM using the modified Friedmann equation. So they're basically just taking what? Why'd they call it f sub 1? Why not f sub 3? Oh, I see what they're doing. So normally, you would have this equation here. The radiation component's not really relevant, so they're throwing that away. They're putting in rho sub m. So normally you would have f of p equals kappa rho sub m. That's what you have. But they're also adding an extra term that corresponds to regular dark energy, a cosmological constant. That's what they're adding here. So that's what this term is, where rho sub dE is the total dark energy density in the universe. This is equivalent to defining f sub 3 of p is f sub 1 of p minus some extra bit. So that's what they're saying. That's all they're doing. They're kind of interpolating between the two. So, and then you write the modified Friedmann equation as f sub 3 of p is kappa rho sub m plus rho sub r as an equation 2. Fine. So when f sub lambda is 0, again, f sub lambda roughly tells you how much the dark energy contributes to the expansion. F sub 3 of p reduces to f sub 1 of p, and all of the dark energy density comes from absorption of baby universes. On the other hand, when f sub lambda is 1, f sub 1 of p is kappa of rho critical. F sub 1. Well, okay, that's just true. F sub 1 of p is kappa of rho critical. And so from equation 7 and equations 1. So which one's equation 7? Equation 7 is this guy. And equation 1, which is this guy. Kappa rho sub dark energy is 3h squared minus kappa rho critical plus lambda. But these two terms cancel out and give 0, so you just get lambda, where rho critical is 3h squared over kappa, that's fine, is the critical density of the universe. So the idea is that when f sub lambda is equal to 1, you just get normal dark energy expansion. This is the same as equation 4, which implies that all of the dark energy density is in the form of a cosmological constant. That's what this is. So basically, when lambda is 0, all of your dark energy comes from baby universes. When f sub lambda is 0, all of your dark energy expansion comes from absorption of baby universes. When f sub lambda is 1, all of your dark energy absorption or all of your dark energy expansion comes from the cosmological constant. And they're saying that this just interpolates between the two by having a variable f sub lambda. So this is the same as equation 4, which implies that all the dark energy density is in the form of cosmological constant. Right, I just read that. Moreover, it is possible to have f sub lambda greater than 1 counteracted by g less than 0. So you can have baby universe emission, so baby universes could pop off, and have more than all of the dark energy available contributing to expansion. With this extra parameter, we will be able to derive limits on the fraction of dark energy that can be attributed to baby universe absorption or preferred models that have the combined two sources of dark energy. Cool. So that's what they mentioned in the introduction, but now I understand what they're doing. All right. Now we're going to do some analysis. This is less elegant than the standard lambda CDM model. However, it might fit the data better because the lambda CDM model is currently fighting against data from the DESI results. So we'll see what they say. The dark energy density of the baby universe models is quite different from lambda CDM at high redshifts, altering the expansion history of the universe. As shown in figure 1, left, there's less dark energy at high Z, which can enhance the growth of structure. Equivalently, the equations of state of the two dark energy models are more negative than -1, as we illustrate in figure 1 right. Let's go take a look at those charts. So here we have figure 1 left. Sorry, I'll zoom back in. So left, we have dark energy density, omega dE, for the pure baby universe model as a function of scale factor relative, scale factor A relative to lambda CDM. So here we have that this is the early universe because we have a scale factor of less than 1. And so in the lambda CDM case, the dark energy is constant. But in the baby universe model case, you have less dark energy in the early universe. And it, depending on which model you choose, it increases at a different rate. On the right, we have dark energy equation of state for dark energy W for on the right, we have the equation of state for dark energy, which is W, as a function of scale factor. So again, for the cosmological constant, again, it's constant. It's just -1. And then you get these W's for these different models. I guess the curves were produced using some best fit data. Fine. By the way, it's not just a lazy interpolation. This is actually based on some kind of a quantum gravity model of baby universe interactions. So there's actually some theoretical grounds here, but I haven't read the original theory papers, so I can't comment on that too much. Right, so they say that so clearly the dark energy behavior, the growth is different in the early universe for these models than it is for standard lambda CDM. The modified background evolution was implemented in the Boltzmann code CAMB. Fine. We do not consider any perturbations in the dark energy density that might arise during the absorption of baby universes, since the description of such processes has not been worked out. Okay, because yeah, you could have dark energy density that's there that might interact with the absorption of the baby universes, which I guess is confusing. But they haven't included that because that's hard. I guess people are still using CAMB. I don't even know what CAMB is. Since the baby universe models provide primarily late dark energy, as is evident here, like the dark energy is weaker in the early universe, one can expect models 1 through 3 to be in good agreement with the CMB power spectrum and temperature autocorrelation spectrum. This will be borne out in the following analysis. Instead, baryon acoustic oscillations and supernova turn out to drive the constraints. Sorry, one moment. One sec. All right. I'm back. I am back. Okay. So first they're going to study the universe with lambda, with the cosmological constant being 0. To incorporate up-to-date constraints on the cosmological observables, we use the publicly available Monte Carlo MCMC. I don't know what that stands for. I don't know, MCMC sampler Kobaya. Convergence of the chains was monitored via the Gelman-Rubin statistic, demanding R-1 is less than or approximately less than 0.02. I don't know anything about this kind of data analysis because I don't do that kind of stuff, but we'll just trust that their statistics are fine. Oh, it's Monte Carlo Markov chain. Thank you. Yeah, I don't do any data analysis, so this is foreign to me. But, you know, we learn as we go. The likelihoods included in our analysis are... Here we go. Here's our likelihoods. These are the R's. These are the best fit cosmological parameters for lambda CDM and the two baby universe models. Model 1 and Model 2 found in the MCMC scan. So the total chi-squared for each dataset is given in the last few rows. Okay, so it looks like lambda CDM is better fit than either of the other two models, which is kind of what was expected. Model 2 is much, much worse. Model 1 is close, but not quite as good as just regular lambda CDM. So, yeah, okay. And they used Planck, they used CMB lensing potential power spectrum, they used BAO, which is baryon acoustic oscillations. And this is the data from DESI. We follow the methodology described in the DESI 2024 paper combining data from DESI and SDSS. So this is the Sloan Digital Sky Survey. And so they're just describing some methods as how they're actually doing this data analysis. They're also using the Dark Energy Survey Year 1 results, which measure cosmic shear and clustering. I guess they're also using supernova data as well. So they have all of these pieces of data. They have the lensing, the supernova, the baryon acoustic oscillation, the Dark Energy Survey, and the CMB. These are all contributing to lambda. So, you know, the supernova and the lambda CDM data are contributing the most to the chi-squared. But, you know, that's okay. And so we computed the chi-squared values for the first two models, which have no free parameters, and compared them. Wait, hold on. Did I miss something? Yeah. Wait, did I miss some text? No, I didn't miss text. Okay. And compared them with lambda CDM. The results are shown in table 1. Fine. Lambda CDM is mildly preferred over model 1, while observations strongly exclude model 2. Okay, so they're saying that, yeah, lambda CDM is better. True. Even though model 1 provides modest improvement over lambda CDM for CMB observations, it's in tension with BAO, baryon acoustic oscillation, and supernova data, which probe the late time acceleration. We repeated the analysis using only SDSS, Sloan Digital Sky Survey, baryon acoustic oscillation data, instead of the DESI 2024 BAO, but obtained similar results as can be seen in table 2. So if you do the same thing, you basically get that, again, lambda CDM is slightly preferred over model 1. Fine. The models become further strongly disfavored with respect to lambda CDM by choosing different supernova datasets, Union 3 and DESI 5, also shown in table 2. So this is saying that if you turn off the cosmological constant, which is what they did here, and just have baby universes, current data just doesn't agree that you should use baby universe. It's close, but lambda CDM is still preferred. Perhaps unsurprisingly, Model 2, which is an early time approximation for the more exact Model 1, fails badly in reproducing late time observations. But even Model 1 is in conflict with BAO observations at redshifts z approximately less than 0.5, as shown in figure 2. So let's look at figure 2. So here we have measurement of baryon acoustic oscillations. Baryon acoustic oscillations are roughly, well, I have a video on this, but it's roughly kind of frozen in spherical waves from the very early universe that froze in because the universe expanded so much that they couldn't oscillate anymore because they were going in and out, pressure waves and gravity. And they kind of got frozen in and then they've expanded. And so the size of those baryon acoustic oscillations tell you something about how the universe has grown over time. And the idea is that you can look at those to try to get into, to understand how the universe has grown. And so they have measurements of baryon acoustic oscillation, distance scales versus redshift. Redshift parameterized as a ratio of angle average distance, this is dB, to the sound horizon at the baryon drag epoch. Don't worry about that. The blue, yellow, and green lines respectively show the prediction for lambda CDM, Model 1 and Model 2 best fit values used to obtain table 1. So the black dots are the actual data, right? And then blue is lambda CDM, and yellow and green are Model 1 and Model 2. Notice that even though blue doesn't agree with the model with this big piece of, you know, the low z value, it's better than Model 1 and Model 2. The Model 1 and Model 2 go down, whereas, you know, the black data point at low Z goes up. So lambda CDM is still preferred there. So where were we? We were here. Comparing to figure 3 of reference 2 based on data listed in table 1, which found a good fit to BAO data, we see that the adopted data look quite different at low Z between that analysis and the present one. The data responsible for the discrepancy are those at low redshift. Cited at low redshift, Z is less than or equal to 0.5 or so. Reference 2 cited surveys dating from 2011 and earlier, whereas we're using references 13 and 14, which are more recent. So basically, they're using more recent data, which conflicts with older data. Hence, our discrepant conclusions relative to reference 2 can be attributed to the fact that the data have evolved since 2011. Fine. Newer data is better data. Generally true. Ooh, these are some pretty pictures. Did I miss something? Oh, yeah. Okay. Next. So they basically excluded the lambda is equal to 0 case. What about the lambda is greater than 0 case? To study the landscape of theories for a universe with both a positive cosmological constant and a baby universe, coupling g greater than 0, we use model 3. We use model 3 to find an equation 9. So model 3 in equation 9 is this one here. So here we have some regular dark energy and some baby universe. Lambda CDM and model 1 are both contained in this description and occur when f sub lambda is equal to 1 and f sub lambda is equal to 0 respectively. We follow the procedure outlined earlier to determine constraints on f sub lambda using Kobaya. The 1 sigma and 2 sigma allowed regions are shown in figure 3 for the 3 choices of supernova dataset, and the 95% confidence CL results, 95% confidence level results are given in table 3. Let's take a look at this figure. So, wait, hold on. Isn't this supposed to tell me about the values of f sub lambda? Yeah, so these are the 1 and 2 sigma allowed regions shown in figure 3 for f sub lambda. So which values of f sub lambda are they? Chi sub lambda. Where's the f sub lambda? Oh, okay, no, I see what... Well, yeah, this is... let's go take a look at table 3. Are you familiar with X-ray scattering dating? I'm not, no. Okay, so here's their data. I see what they're doing. Okay, so they first fit f sub lambda. They weren't showing us that in the chart, but the best fit cosmological parameters for baby universe model 3, including a cosmological constant greater than 0, we get that if we use the Pantheon Plus data, we get 0.86. If we use the DESI 5 data, we get 1.18, and we get the Union 3 data, we get 1.17. And then we get the delta chi squared is minus 1.3, minus 6.8, and minus 1.6. And so I guess those are the different parameters of the Hubble constant, by the way, which is actually really good because that might fix the Hubble tension. And didn't they say that? Yeah. So here we're looking at marginalized posteriors for f sub lambda, h naught, and sigma 8, which is okay. So it's this guy. So, which ones? Okay, so we have Pantheon, DESI, and Union 3. So it looks like we're seeing that there's a lot of overlap between the DESI and Union 3, and not a lot of overlap between Pantheon, but there is still some overlap there, which is good. Because it means that that there might be a choice that's compatible with all 3. Somewhere like right around here. All right, let's keep reading. Where were we? In addition to f sub lambda, we show distributions of h naught in the clustering patterns S8, which also has exhibited a mild tension between early and late time observables. The estimated lambda CDM value, S8, from Planck is in the 3 sigma tension with the KIDS 1000 reported value. The best fit DESI 5 curve reduces the tension to the 2 sigma level. So that's good. I mean, if we look at the... Oh, they don't include it in the table. Okay, never mind. Yeah, okay, they don't report on the table, but yeah, I guess that so yeah, the point is you want to compare these two as opposed to these two. That's roughly the idea. And so the Desi 5 curve does fit the data better if you use f sub lambda. So that's a good thing. Pantheon plus looks sus. Maybe. But it's a data set. You can't throw away data just because you don't like it. Using the Pantheon plus supernova data, the results indicate that most of the dark energy today is in the form of a cosmological constant, with only a small fraction of dark energy, if any, coming from the merging of baby universes. The pure baby universe scenario, f sub lambda equals 0, is disfavored by more than 2 sigma. Yeah. The best fit value from DESI 5 indicates that f sub lambda is approximately 1.2, which is, indeed, greater than 1, which implies that the baby universe coupling constant is less than 0 to maintain spatial flatness. This corresponds to... Sorry, I have to go blow my nose. My nose is so itchy. Sorry about that. You know, if I had allergies, I would blame allergies, but I don't have allergies. Right. Where were we? The best fit value from DESI 5 indicates that, right, so we have 1.2 is greater than 1, true, which implies that the baby universe coupling constant g is less than 0 to maintain spatial flatness. This corresponds to a universe with excess cosmological constant that is compensated by the emission of baby universes. So what's happening is there's more cosmological constant than there should be, but also the universe is giving off baby universes, which is a fascinating idea. Because maybe that's how new universes are born. Maybe that's how our universe was born. Who knows? The full dataset, plus DESI 5, offers a significant improvement over lambda CDM, with delta chi squared being less than 6.8 as shown in table 3. The equation of state of model 3 with lambda greater than 0 is close to -1 as shown in figure 4, because most of the dark energy is coming from the cosmological constant, with only a small contribution from the exotic dark energy source. Let's go look at figure 4. So the red line has a W that's basically -1, but it slightly changes over time. Ever so slightly. Okay, what about the other case? Next, we consider model 3 in the region of parameter space where the cosmological constant is negative. Following the same procedure as above, we find that this can provide a significantly better fit than lambda CDM when using the Pantheon Plus dataset as shown in table 4. Where's table 4? Where is table 4? Table 4. Okay, so here, the best fit data, we have a really good best fit with a delta chi squared of -8.5 using the Pantheon Plus dataset. Hardly better, though, for the other datasets. So, Pantheon Plus may be a little sus. I don't know. In figure 5, we plot the CMB matter power spectrum predictions for model 3 and the lambda CDM best fit. So that's this plot. So this is the power spectrum. And then they have the lambda CDM best fit in blue, which is pretty damn close. It's almost perfect, actually. This was one of the successes of lambda CDM. And then model 3 best fit, which is also very, very close. However, these extra points over here at the end are not fit by either of them, which is very bad, by the way. Well, it's not that bad, but it is kind of bad. Right. From the residuals, one sees that the improvement in chi-squared is due to the intermediate scale, which is right around here, between 10 to the -3 and 10 to the -1. These are just the residuals, what the difference is, right? I'm just taking a look. Yeah, so there's some bad residuals here in this region, but there's significant improvement here. We noticed that the dark energy equation of state, W of A, for model 3 with negative lambda has unusual behavior, diverging at A approximately 0.1 before entering the phantom-like regime with W is less than -1. This is due to the dark energy contribution changing sign, while its pressure remains negative. In figure 4, we compare W of A of the two scenarios to the Barboza-Alcaniz parameterization, which has this form. So let's go take a look at figure 4. So, yeah, this is really weird. So here you have the negative lambda best fit. You have your equation of state going upwards towards infinity at like A as being 0.1. And then it is negative infinity slightly after. That seems super unphysical. Super unphysical. When that kind of thing pops up, you know something's wrong. This parameterization was shown in reference... Oh, actually. No, never mind. It's fine. This parameterization was shown in reference 27 to give an optimal fit to data with respect to the recent DESI BAO indications of evolving dark energy. Okay. That's quite recent. And so this is just, you have stronger dark energy and then weaker dark energy, roughly. So, the preference for Model 3, however, is not robust against choosing a different supernova dataset, such as DESI 5 or Union 3, as demonstrated in Table 4. Pantheon Plus and Union 3 have roughly 1360 supernova in common, but differ in their analysis and methodology. DESI 5 has 194 supernova in common with the two, but has an additional 1500 photometrically classified supernova type 1a at higher redshifts. In the concluding section, we comment on a possible explanation for the discrepancy between the DESI 5 and other supernova datasets. In figure 6, we compare the distance modulus predictions for Model 3 for the two cases against lambda CDM. Let's go look at, let's read this paragraph and then we'll go look at figure 6. One sees that the improvement in chi-squared for lambda less than 0 comes from intermediate redshifts, z between 0.1 and 3. For lambda greater than 0, the slight improvement in the fit is due to the outliers in the data. Okay, so this is the distance modulus predictions for lambda CDM, green best fit curves. So red is, so this is the lambda less than 0, this is lambda greater than 0. So they said that when lambda is less, so here we have a significant divergence at big redshift. Whereas, which may match the data better, whereas in red here, it's like basically the same. I don't really see what the difference is. A little bit suspicious. So they say that for lambda less than 0, it comes from intermediate redshifts. So z is 0.1 to 3. So z is 0.1 to 3. So out to here. So this is like in this range, I guess. And then in the lambda greater than 0 case, the slight improvement in the fit is due to the outliers in the data. So they're just saying, look, there's outliers here. Like outlier here, that's making it, the red one is slightly higher than the green one, so that's making it slightly better fit. Figure 7 shows the marginalized posterior on F sub lambda, H naught, and S8 for the different supernova dataset choices. It demonstrates the preference for F sub lambda being negative between negative 0.5 and negative 0.1, and values of H naught closer to the supernova preferred value in the case of Pantheon Plus data. Values of S sub 8 is less than or equal to 0.82 are preferred in this case. Let's go look at figure 7. Okay, so they're saying it's like in this range here for F sub lambda is preferred, and then for H naught you're getting like 69.5 or so, and then for S sub 8 you get like, I don't know, 0.81 or something. Yeah, okay. The value of the Hubble parameter obtained in the full MCMC scan for Model 3 with negative lambda is 69.9. Hey, that was a good guess. 69.9 plus or minus 1.1 kilometers per second per megaparsec with 95% confidence interval. The latest distance ladder measurement of H naught by the Shoes collaboration is 73.2 plus or minus 1.3 kilometers per second per megaparsec at 65% confidence interval. Thus, Model 3 alleviates the Hubble tension to within 2 sigma of the local measurement. which is good. The best fit S8, 0.803 plus or minus 0.018, also eases the tension to within 1 sigma, which is huge because those are the two biggest cosmological issues right now. I may have developed allergies. I hate that a lot. So now we just have the discussion. In this paper, we have systematically scrutinized the baby universe absorption model for accelerated expansion of the universe as proposed in references 2 and 3, which I'm going to read probably tomorrow. Using data from various experiments, we were unable to find a preference for either of the two pure baby universe models over lambda CDM. We also reevaluated the chains using different supernova and BAO datasets, but all of them reiterated the same fact. Fine. Allowing for the cosmological constant to be different from 0 using the new parameter f sub lambda that we define as the fraction of the dark energy density in a cosmological constant lambda, we find 2 allowed regions of parameter space, one close to lambda CDM and another with negative lambda. Both the regions are excluded to the point f sub lambda equals 0 with 95% confidence interval, which corresponds to a pure baby universe model that was initially proposed. The former has a delta chi-squared of minus 6.8 using DESI 5 supernova data, while the latter one has a delta chi-squared of minus 8.5 using Pantheon Plus data. Both models are therefore significantly preferred over lambda CDM. The latter one predicts a higher value of H naught, 69.9, and thereby ameliorates the Hubble tension to within 2 sigma of the local measurement. That's nice. Recently, it was suggested by the DESI 5 supernova data that the DESI 5 supernova data may suffer from a systematic 0.04 magnitude error in going between low and high redshifts. Oh, that's not good. I haven't heard about that. Which is not observed in the Pantheon Plus data. And correcting for this removes the evidence from DESI BAO measurements for evolving dark energy. Oh, what? Hold on. What's this reference? I'm going to look at that because that's interesting. On this basis, one might doubt the preferred region we found for lambda greater than 0, which is driven by the DESI 5 data. However, our other preferred region, with lambda less than 0, is instead driven by the Pantheon Plus data, which does not suffer from this caveat. Although the lambda negative baby universe model is not economical, needing 2 separate sources of dark energy, it makes the interesting point that an unusual equation of state dependence, having a pole at some early value of A, can give a good fit to present data. The divergence is a consequence of the dark energy density changing sign at some redshift, even though the total energy density remains positive. Such behavior is not captured by standard parameterizations of W of A, such as those considered in reference 27. What does that mean? The dark energy density changes sign, even though the total energy density remains positive. Ah, I see. So the dark energy goes from negative to positive, but the total dark energy, because there's other stuff around, is still positive. And, okay, that's the end of the paper. Okay, so I think it would, I think this paper is interesting. I think it would be at least more interesting to me if they actually elaborated on what it might mean to have an equation of state with a pole in it. I mean, they do say that it's the consequence of the dark energy density changing sign at some redshift, but why would that happen? Like, is the dark energy density decreasing, passing through 0? Yeah, it could be doing that, actually. Maybe that's what it's doing. Well, okay. So, not going to give this a rating because I've stopped doing that because it might offend the authors. But I like this paper, and I'm actually going to go do some reading, and it gave me some good references to look at. So, to everybody who's been watching, thank you. Thank you for enjoying. I hope you did enjoy. If you missed it, if you missed the beginning, feel free to go back and rewatch it. It'll be on YouTube probably tonight or tomorrow morning. So, if you don't see it now, go see it then. And to everybody who's watching on YouTube, of course you're watching this now. So, bye!